Hey guys, I wanted to do a quick video on single displacement net ionic reactions and how to write the half reactions as well. I know one of the videos talks about the half reactions, but I just want to do it based upon these net ionic equations to help you guys out. So we're going to go through one or two examples to help you get the hang of everything. Now, the way you work these net ionic reactions is pretty much the same exact way that you would write the net ionic reactions for double displacement reactions. The only difference is double displacement reactions is where they're switching partners. Single displacement reactions is when you have a single element that is going to switch with a compound. So let's get into it. First of all, what we have to do here is predict our products. So we have manganese and lead to nitrate, okay? And so when these switch partners, the manganese is going to combine with the thing that has the negative charge. The reason why is because Mn is a positive charge because he's a metal. He's a cation whenever he combines with a compound. So the Mn is going to get with a nitrate, and what that's going to do is kick out the lead by itself. So when Mn gets with a nitrate, we have to know what are the charges of Mn to be able to write that compound correctly. Now, Mn is a transition metal where it has different charges. It's not one set charge in the column. So what we have to do is have some other piece of information to tell us what charge it will be whenever it combines with nitrate. So I know that Mn has a couple of different oxidation states. I'm just going to say, hey, this is going to create something that has an Mn with a 2+ charge. So my first product here is going to be Mn with a 2+ charge combining with nitrate, which is a -1 charge. So that's going to be MnO3(2). This 2 comes from the fact that Mn is a 2+ charge, which I would have some piece of information on the AP problem to help me realize that. Then we have to write our other product, which is Pb. So Pb is kicked out by itself, so it's going to make Pb like so. Okay, so we have predicted our products. If you want to, you can go ahead and balance the reaction, which it looks like it's good to go right here. Okay. Now, our next step, just like we did for this double displacement net ionic equations, is going to be able to assign solubility. Now, if you have an element that is by itself, that thing is going to be a solid. Okay, that's just manganese, the metal, it's a solid. Lead to nitrate, according to solubility rules, is aqueous. Manganese to nitrate is also aqueous, and how I know that is my solubility rules. Nitrates are always soluble, and Pb is knocked out by itself, so Pb is just going to be a solid. So I have assigned my solubility to each compound here. Now I have to figure out my spectator ions. So do you see how nitrate is aqueous here, and it's also aqueous here? So he is going to be a spectator in the reaction. Now what we do is bring everything down. So you have to be careful and pay attention to the solubility you assign each one. If it's a solid, it's just going to stay by itself. But if it is aqueous, I have to represent it as its ion. Remember, we had to do that for our double displacement reactions as well. So we're going to bring Mn down. So that's Mn solid. Plus Pb is brought down, but Pb is going to be represented as its charge because it is aqueous. Do not forget this. If I write just Pb, that will be wrong. Yields Mn, since it is aqueous, we have to represent it as its charge. And Pb solid is going to stay like it is down at the bottom. So what I have here is a balanced net ionic equation. Okay, so this is how we work our single displacement net ionic equations. We have our things here, that is all good and balanced. Okay, now I want to talk about how to write a half reactions. So we have two different half reactions that we have to write. One is called an oxidation half reaction, and the other one is a reduction half reaction. Remember, oxidation is losing electrons. So what is happening to the transition states? To the oxidation states of our compounds? Because we're losing electrons, my charge, my oxidation state is getting more positive. The reason for that is because electrons are negative, and if I'm getting rid of negatives, then I'm going to make that species more positive. So my oxidized species is going to be Mn, because Mn goes from a 0 oxidation state to a 2+ oxidation state. So for my oxidized reaction, we are going to say Mn yields Mn2+. Now, in our half reactions, we have to be able to put the electrons that are transferred there. So if we look at Mn to Mn2+, we see that our charge is changing from 0 to 2+. That means we have transferred 2 electrons there. So we have to put these electrons in the half reaction. Now, the question is, which side do we put those in? We will always put it according to the side to balance our charges. So what that means is, over here I have an overall 0 charge. Over here I have an overall 2+ charge. Well, I need to make either this side 2+ or this side 0. Well, I can't make this side 2+ because there's nothing that I can add there. But I can make the overall charge of this side to be 0 by adding the 2 electrons on this side. Because what this is doing is making 2- and 2+, and that cancels out to be 0. So this is my balanced half reaction for the oxidation. Now we're going to do the half reaction for the reduction. So we look here. Reduction means that you are gaining electrons. Because you are gaining electrons, remember, electrons are negatively charged. What you're doing is you're getting your charge, your oxidation state, to become more negative because you're adding more negatives there. So, do you see how this Pb goes from an oxidation state of 2+ to 0? This is getting more negative, which is what's happening when you're gaining electrons. How much are we changing my oxidation state by? We're gaining 2 electrons. So if we gain 2 electrons, then I have to be able to write my reduction half reaction here. So I have Pb2+ yields Pb. And I have to add my electrons in here in order to balance my charges. Do you see how I have a 0 charge here and I have a 2+ here? So my 2 electrons are actually going to go on this side. So therefore I can have an overall 2- and 2+ 0 charge here, which balances with the overall 0 charge here. So this is how we write single displacement net ionic reactions, oxidation half reactions, as well as reduction half reactions. I might create another video to show you guys another example.